And now we're recording because we're done going over the quiz, and we will start talking about the material for today. Last time we started talking about the B tree, talking about the motivations for the B tree, and the rough idea of what its structure looks like. The motivation is that in the data structures courses, we talked about binary trees, which are great for in-memory access. You get the logarithmic access time. But when you're talking about disks, we don't care about the CPU operations. We care about the total number of disk I/O operations. And the B tree is designed to minimize those disk I/O operations. And the way it does that is it has this large fan out. We'll be using this B variable to measure the fan out. And that means that the tree is going to be a very fat and short tree. Short is good because the total number of disk operations that we're going to do is whenever we do a search, is going to be the height of the tree because we'll have to inspect every particular node. And we saw that we're trading off here between the total number of CPU computations versus the number of disk computations. The total number of CPU computations was the B log B times N. It has this extra B factor out front, but the total number of disk operations, HDD seeks, log base B of N. And so even though this over here is guaranteed to be bigger than for a binary search tree, because this is the thing that we really care about, the HDD seeks is what we really care about. We want to minimize that as much as possible. And so having a large B value is good for a on-disk data structure. We also mentioned that for Postgres, the way that the B value is determined is that we just fill up a page with as many things as we can. And so the typical B values is somewhere between 100 to 400. And so even for like extremely, extremely large data sets, like the entire internet, if you have, say, 10 to the 15 items in your table that you're trying to index, the height of this tree is only going to be like 4 to 5 layers tall. And so it's really only 4 to 5 disk seeks that we have to do. And so it's going to be very, very efficient. So that's the super fast high level overview of what we talked about last time. What we're talking about this time is actually working with these in Postgres and Postgres' implementation of B trees. Before we get to that, any questions about anything? Okay. So, turns out there are many different sort of subtle variations of B trees. We'll talk about the particular choice of why Postgres does things in a little bit, the way it does. But first I want to highlight that the actual official docs for the Postgres B tree, extremely, extremely terse. It's only these 2 paragraphs right here. So if you don't already know what a B tree is, this is not going to help you understand what a B tree is. And so because of that, our main reference is going to be this haber.com webpage. And again, last time I mentioned that this is a Russian webpage. And I do want to say one more thing about why I think it's good to collaborate on scientific matters between people who are not friendly with each other. So Russian's not particularly friendly right now. And this guy, Jeremy Stone, is one of my heroes. I'll just say like 30 seconds about him. But he was a math professor at Pomona College. And he also arranged a whole number of scientific exchanges between the US and Soviet Union during all sorts of conflicts with the Soviet Union. So like Vietnam War, Korean War, Soviet invasion of Afghanistan, Czechoslovakia. But because of those scientific exchanges, a whole bunch of treaties that came about, like the Anti-Ballistic Missile Treaty and the SALT II and SALT I and START II treaties limiting nuclear weapons. That having the scientists and engineers actually working to each other help the diplomats sort of come to their senses about things. So I think it's actually good for us to be using these Russian documentation and working with the Russians on these particular things. So this will be our main reference. It doesn't actually have all of the details though. The main, if you really, really wanted the nitty-gritty details, the Postgres actual source code is extremely well documented. Postgres is famous for having very well documented source code. So clicking this link takes us to the actual implementation of the btree in Postgres. And the README file right here has the actual like detailed explanation of how the btree works in Postgres and all the Postgres like subtleties about it. So this is the gold standard of if you really wanted to know how things work, that's what you would reference. For our class, so you don't need to look at that. Okay, so now we're going to talk about using the btree for our actually making our select queries fast. Any questions before we get into that? Okay, so the basic idea. You will be writing select statements that describe what you want. We've already talked about how to do that. And then in Postgres, there's this thing called a query planner, which is automatically going to determine for us how to go about calculating whatever it is that we're trying to compute. The query planner is a very complex piece of software. The internals of Postgres, chapter 3, which you don't need to know, goes over the details of the query planner. But at a high level, what the query planner is going to do is it's going to rewrite your SQL query into a more efficient expression, if that's possible. So we talked about before how the outer joins can be equivalently written as a not in expression. And sometimes doing it as the not in is more efficient. Sometimes doing it as an outer join is more efficient. The query planner will automatically determine for you which one of those is more efficient and rewrite it for you. So you don't really need to think about the details too much. It'll, as long as you write the what correctly, it will figure things out for you well. And it's going to give you sort of the best algorithms for your particular combination of hardware and data and the different indexes that you have and whatever it is, the select statement that you're running. So it really is like, I don't know, I think a pretty magical piece of software. It turns out that there are various theorems that say that in general, you can't perfectly do this step so that you get the exact most optimal thing in all circumstances. But really the edge cases where this happens are like really pathological and don't come up in practice. So you're going to get really good query plans like on anything that you actually care about in the real world. But if you did want to know the details about how this works, how query planning works, a compilers class is what would cover those details. So in order to figure out the one thing that we will need to know about the query planner is to figure out what the query plan was that it actually chose to use. And the explain command, we'll go over this next in Postgres, the explain command will tell us how to do that. And this will be our key tool as we're debugging all of our performance problems in class. So I'm going to come over to the terminal over here, and I'm going to just double check to see, am I recording right now? I am recording, okay. But I'm not sharing my screen, that's why it's not doing it, dang it. Share my screen. Apologize to everybody who was on Zoom. We were just going over all of the things in the notes at this point. And now we're getting into the terminal over here. And it's the explain command that we are looking at next. And anytime you have, well, let's see, yeah, before I talk about the explain command, let me just talk about what's the environment that we're in right now. I'm currently in my Twitter Postgres parallel folder in my solution. So this is the assignment that if you're collaborating with people is due tomorrow. And we're going to be looking in particular at this tweets table like this. And this tweets table currently has no indexes on it. Your solution might happen to have some indexes on it. My solution has no indexes on it. And but it has all of these columns over here. And let's say I want to do something like select id tweets from tweets where the language equals English, like this. So this seems like a reasonable query that I might want to do at some point. And this is actually a part of some of the test cases. But this is basically getting all of the tweets that are written in English. And if I hit enter, it'll go ahead and compute that for me. But if instead of just hitting enter, if I take the word explain in front of that, it's not going to run this command here. It's only going to run the query planner and tell me the output of the query planner. So I'll hit enter like this. And this, it tells me right here, this is the algorithm that it's currently choosing to use to implement this query right here. And so the default algorithm, anytime you have, basically anytime you have anything, is going to be this sequential scan. The sequential scan doesn't require any indexes. It's something that you can always do, and so that's why it's the default algorithm. And we'll talk about this here in a second. But before we do that, any questions on just the syntax of this explain command? Okay. So what we're going to talk about next is the different table scanning strategies that Postgres uses. So there's 4 of these strategies, and the table scanning strategies are for how the query planner implements queries that look like this, like sort of the simplest, most bare bones query that you might want to do. Select something from table where condition. And so this again is this pattern matches this select query that we just typed in, select the id tweets from tweets, and then our condition language equals English. And we're going to talk about the 4 different algorithms that Postgres can use to implement these this query right here. And in order to do this, we're going to talk about their runtimes. We're going to need these different definitions up here. Actually, let me refresh this real quick. There's 4 variables up here that are in use. So in will be the total number of tuples in the table. A, the number of tuples per page in the table. So we've seen before that the A, like the number of tuples per page, is actually going to vary depending on the size of the tuples and the insert, update, delete order. So this is a very sort of abstract thing, assuming that they're all going to have the same number of tuples. Similarly, the branching factor B of any given btree, the branching factor is going to depend on the actual size of the tuples, and so we can't necessarily say that they're all going to be B, but just for analysis purposes, we'll make that assumption. And then K, the total number of rows returned by our select statement. And as we see all of these formulas, I'll remind us about what all these variables mean when we get to the context. But this up here at the top is the where you can look up to see these definitions. So again, the sequential scan is the first of these algorithms. We know that over here we're using the sequential scan because it says seq scan right here, seq short for sequential. And there's no requirements on when this algorithm can be used. It can always be used. The disadvantage, though, is it has a really, really slow runtime. The total number of pages that you're going to access is potentially all of the pages. And in this case, though, the number of index pages that you'll access is 0 because we're not using an index. And the total, there's 3 things that we're going to track for all of these operations. So disk accesses on the table, disk accesses on the index, and CPU operations. And again, the thing that we care about is the total number of disk operations. The total number of comparisons, much less important. But in this case, if we're doing a sequential scan, we'll have to, whatever our where condition up here is, we'll have to apply that to every tuple in the table. And so, maybe an advantage here, though, is that it's a really small constant factor, that there's no like tree traversal overhead or anything. So it is O of n, but it's a small constant factor or O of n. And the main time when this is going to be used is when there's no index defined. We'll talk about some of these other ones in a little bit when we talk about the limitations of these next scanning techniques. Any questions so far about the sequential scan? Basically just a for loop over the pages. Yeah. Question is, yeah, why is the number of table pages O of n? We can make this actually a little bit more tighter bound by saying, you're right, that if we have A is the number of tuples per page in the table, then we could do something like O of n over A to make this a tighter bound. O's are upper bounds though, so this is anything that's O of n over A is also O of n. Yeah, so you're right, this is a true statement. It's maybe not the most tight true statement that we could say though. Did that answer your question? Good question. Any other questions about the sequential scan? Okay. So the other three types of scans are scans that involve indexes, and roughly all of these are going to convert our linear runtime down to logarithmic runtime somehow. And so we're going to need to be paying attention very closely to when all of these index types of scans can apply, so that we can very carefully decide which types of indexes to create for our tables. At this point, we're not going to go over in detail this, this set of notes over here, but at the bottom of this set of notes where it says integrated questions, these are the sort of, this is the sort of knowledge that you'll need to be able to know to answer this type of question. So probably next class we'll get to actually talking about some of these questions down here. But that's what we're building up to. So the index-only scan. First, let's talk about how you can actually create an index. So if we do create index is the name of the command, and then we say on the name of the table. In this case, we'll do tweets, and then the list of columns that you want to create your index on. So here we'll do laying like this, creating an index on the laying column. What this means is that in the, a lot of windows open right now. Over here, in our in our actual btree, the things that are stored in the btree are going to be just the languages like EN or DE or whatever our language codes are. And then maybe over here, we might have like, so AR and CZ as things coming off to the left of English. And those are the only columns stored in the index itself. It's not going to store any of the other columns over here. And so when we have an index-only scan can be used whenever the index is what's called a covering index. A covering index means that in our select query, the where clause only references things present in the index, and the columns returned are only in the index itself. So over here, if I were to do something like select language from tweets, where lang equals English, like this, here the list of columns over here is contained in this column list. The conditions over here contained in this column list. And so I can hit enter. It's just going to be a whole bunch of Englishes, so not a super informative query at this point. But if I do explain like this, we'll see that it will say index only scan over here. And it's able to use the index only scan again because the conditions, all of the columns mentioned, match what's inside of this, this column list up here. If I wanted to have multiple columns being returned, for example, so let's make this a little bit more of like a useful query, something like id tweets, lang, so actually get like the identifier of the tweet and the language. This we cannot use an index only scan on this particular index right here because this index only supports the lang column. In order to use, go ahead, hit enter, Q. In order to use an index only scan on this query right here, because it has both of these two things here, I would need to, when I run my create index command, add other columns to this index here that I might want to extract. Language, comment, it tweets like that, hit enter. Now, when I come up here and do an explain on this, we can get our index only scan again. It will become important in a little bit to think about the disadvantages of putting too many columns up here, or the potential trade-offs of the order of those columns, but we're not going to talk about that yet. The main thing at this point is that in order to use an index-only scan, all of the columns referenced must be contained up here. Any questions about that so far? Okay. In order to, let's see, so if we reference a column that's not contained up here, so let's say id users instead of id tweets, oops, in our select statement, do id users, comma lang, like this, you'll see that we no longer are able to use an index only scan. In this case, we get the bitmap index scan. I'm going to change this to, yeah, let's see. I'm going to do, so backslash D, and then the name of the table will tell us all of the different indexes that we've created so far. We have 2 indexes down here that we've created. I'm going to drop this index, get rid of it so that we can see what the next index scan type is. Drop index that, like this. That gets rid of it. And now when we, I'm going to rerun that. Explain id tweets, lang from tweets. And I want to do where the language is equal to AM, like this. So AM stands for Amharic. It's a Semitic language similar to Arabic and Hebrew. Turns out there are only 2 tweets with that match this in the data set. But here you can see again, so id tweets and lang, so we're using an index scan instead of an index only scan. What we're going to talk about next is the actual, like, physically what's going on in an index only scan versus an index scan, and how that affects the runtimes between both of these 2 operations, and how that affects, like, our choice of which one we should want to use. At this point, all we've talked about is the conditions on when one of these is applicable and when the other one is applicable. If, yeah, I guess I explicitly said that the index only scan, the conditions up here must match the index, the columns must match the index in both the what's being selected and the conditions. For an index scan, it's only the conditions. Only the condition must match the index. Index only scan, condition and column list must match the index. That's the difference. In an index scan, the way this is sort of physically implemented is inside of Postgres, in our btree. Postgres technically uses what's called a B+ tree inside of its btree index. Everywhere in the Postgres documentation, it refers to the btree index as a btree index without the plus. Technically, it's a B+ tree. Sort of theoretical sources like Wikipedia, textbooks, sometimes make a big difference between B+ trees and B trees. In the real world, they're so similar, nobody really cares. But technically, a B+ tree only stores data in the leaves of the tree. And in Postgres, what data means, data is the TID, the tuple ID of whatever tuple corresponds to the particular data in our data sets. So here we created an index on the the language. So any of our non-leave nodes up here, these are only going to contain languages. And they could be duplicated. So we might have something, there's a lot of Englishes. So we could have, say, multiple Englishes up here. And then we'll go straight to, we'll do French like this, FR, leave that one empty. And then over here in the actual leaves, this will be a leaf right here. And the leaf will have both the value of whatever the column is. So if we had AM like this, and then it'll also have the tuple ID. And recall that a tuple ID has two numbers associated with it. It'll look something like 3, 7. The first number is the page number that the tuple is located at. And then the second number is the tuple number in the page. And then this whole thing right here is the TID. And so there's maybe AM, and then, well, it turns out, yeah, there's 2 AMs in this particular data set. We'll have another AM like this with a separate tuple ID of maybe 5, 3. And then we'll go up to, say there's a German DE, has its tuple ID of 1, 6. And yeah, then we'll stop there. Over here, there'd be anything between English and English. These would all have to be English ones. And those would all have tuple IDs associated with them, whatever they might be. And so on. And so in an index scan, the way we get the information that we need is we go through the index, find all of the tuples that match our condition. So here we looked for the language equals AM. So that would give us, it would identify this position and this position right here. So it would identify these two particular tuples that we need to look at. And then once we have that list of tuples that contains the information that we need to look for, we go to the table and index scan, go to the table and directly look up the info from the TID. Because the TID is like the physical location on the hard drive where we can find the particular information. And given this TID, we can get any of the columns associated with these particular tuples. And so this is going to give us all of the tuples with language of AM, and we can find whatever other information we need about it this way. Are there any questions about how that index scan works? Question is, what about nodes that are not leaves? The answer is that every tuple, let me write this out. Every tuple in the heap has exactly one leaf associated with it, and vice versa. Every leaf node corresponds to exactly one tuple. The non-leaf nodes have no TIDs in them, have no TIDs, so they don't correspond to physical rows. No. actual physical rows, and they only exist for the like structural purposes of letting us do the binary search to find it. To facilitate the binary search. And again, technically, this is the property that makes it a B+ tree instead of a B tree, is that only the leaf nodes have the TIDs. The reason Postgres makes that decision of only having the leaf nodes be TIDs is because the TIDs take up a little bit of space in the page. They're two 4-bit integers, so that takes up 8 bytes each. So if we had 100 of these in, that's 800 bytes. That would reduce our branching factor, and we want to maximize our branching factor in this B tree. And so because of that, they chose not to include the tuple IDs up here. The fact that the tuple IDs are only contained in the leaves is a pretty minor detail, but you'll see it mentioned in the docs and in all the references fairly often. Good question. Any other questions so far? Okay, then, so in order to do a index scan, we'll get to the index-only scan here in a second. In order to do the index scan, the number of table pages that we're going to access is going to be the total number of TIDs that we match, the total number of elements that we're returning. And so back over here, in this case, when we searched for AM in this particular tree, there were 2 results down here. So we're matching to 2 different TIDs, and so we're going to look in 2 different table pages. So in this case, the K value is equal to 2. K is equal to 2 for the language equals AM query. 2 TIDs match. And we have to actually physically visit those pages on the hard drive. And so our table pages O of K. And this is as tight as you can get. So technically it'd be theta K. One of the downsides of the index scan, which we'll see in a little bit, is that there's no guarantee that the same page will not be accessed multiple times. And so with the English over here, there's going to be a lot of different English queries. Let's add one more English right here. And here we have each one of these 3 tuple IDs sits in a different page. If we come back, this one over here has TID of, say, 4,7. This TID, this one, and this one here, they sit in the same page. But Postgres is not going to be able to take advantage of that fact when it uses the index scan. It's going to just go down this list, look at this page 4, then examine page 10, examine page 13, and then re-examine page 4 from scratch. So we're going to, however many entries there are here, we're going to examine the number of table pages exactly that many times, possibly duplicating ourselves many times. The total number of index pages that we'll access. So here, the log base B over N corresponds to doing the binary search down to the particular location that contains the node of interest. And then this K over B here corresponds to, so if the number of entries that match our condition is greater than the branching factor, then we might have to access multiple leaf pages. So down here, there's just one English page here right now, but there could be multiple English pages, and in fact, there would be in our real table because there's so many English entries. Add some more English. And so we'll have to access this leaf page and this leaf page here. So the log factor comes from doing the binary search. and then the K over B factor comes from there might be multiple leaves that we have to actually access. So this, though, is still going to be like really, really good compared to a sequential scan, as long as our K value is relatively small. And in particular, as long as our K is significantly less than the N over A, then the index scan is going to be a lot better than the sequential scan. If K happens to be greater than N over A, so we're basically accessing everything in the table, then the index scan is not going to give us any speed up, and the sequential scan would be preferable to the index scan. This is a key thing to make sure that you're understanding so both the number of table pages accessed, O of K, and the index pages accessed of log Bn plus K over B. So if you have questions about either of those two formulas, now would be a good time to ask them. Are there any questions about that? How's everybody doing? Is it everything making sense so far? Yeah. Question is, are the table pages accessed actual like I/O operations? And that's the right way to think about it, is that we've done an I/O operation actually touching the hard drive and pulling the information out. That technically the operating system can mask some of that. So if you access the same page like right next to each other, the operating system will cache that for you, and you won't technically be accessing the hard drive each time, but there's no guarantee about that. And so you should think about it as like physical touches to the hard drive. Yeah, and so that takes like milliseconds each time, and so we really want to minimize that number. And so like, yeah, OK, if K is just 1, this is really good. That's the minimum possible thing. So if we have a really selective query, it turns out that where language equals AM, this is a really selective query because there's only 2 things that match this. Select count star from tweets where lang equals AM like this. There's only 2 things that match this. So this is a really selective query. And an index scan makes sense for that. It turns out that if we change this to EN, let me do the count first. Where'd the count go? Select count star from tweets where lang equals EN like this. There's a lot, about half of the tweets are written in English. And so an index scan does not make sense for that because we would have to touch 40,000 different pages, which is a lot more than the total number of pages that are even in the table. And so a sequential scan is going to be faster than an index scan on this particular condition. There's a third type of index scan, which we'll see in a little bit, that is better than the index scan for that situation. But yeah, we would not want to use the index scan on that condition for that reason. So we have enough time to finish talking about the index-only scan up here. The difference between the index-only scan and the index scan, performance-wise, is that the number of pages accessed, you'll see, pages accessed, exactly the same. The comparison operations, exactly the same. Index pages accessed, comparison operations accessed, exactly the same. The difference is that the table pages accessed is going to be 0. So the index-only scan, potentially much faster than the index scan, especially when K is large. Because for the index scan, the number of pages accessed is O of K. The way the index-only scan works is that if all of the information that we need is actually already contained in the index up here, then we don't need to look at the tuple ID and go find the corresponding entry, the corresponding tuple in the heap table. In this case, so our example index so far, the tweets, this btree exists only on the lang column. So that would be the select lang from tweets, where lang equals am, some like really dumb query like this. We do that, again, we can have the index only scan because the thing that we're selecting right here, all of this exists inside of the table. We also created the, we created this second index that we dropped later, but the language and the id tweets like this. And if we do this, now each one of those nodes is going to contain both the language information and this ID tweets inside of the node itself. So back over here, when we're drawing out what the btree actually looks like, now the information contained in each one of these entries in the btree, I think I can fit it in here. It's going to contain first the language, and then it'll contain like the ID number. And then say 1024. And the it's going to, whatever the column order that we used in the create table command down here, it's going to use the same column order over here. And whenever it does its sorting and whenever it does its comparisons, go left or go right, it'll go first by the leftmost entry. And then if the leftmost entries match, it'll go on to the next entry over here. So here the two Englishes match. So this 37 must be less than this 1024. But then if we had our, say like French right here, this French one could be whatever number we wanted, 57, whatever the tweet ID is. And this one doesn't have to be less than this one right here because the French tuple is greater than the English right here. And now with a tree that contains all of this information down here, we still have our AM, and this is maybe tweet 75 and AM 90, and then jumping up to English 3, and so on. If we're looking for the tweet IDs corresponding to these particular languages, we no longer have to go actually look at the heap table because the tweet ID is already contained in the btree up here. And because of that, we can avoid a lot of table accesses. So that's the main advantage of the index-only scan. Main advantage of the index-only scan is that the number of table accesses will be 0. Disadvantage, though, is because we're storing more information in each of the nodes, the branching factor is going to be smaller. But that's usually pretty negligible. Any questions about that? Okay, the next time we'll start seeing how all of these things impact the notes over there, creating the indexes to get our particular queries to run fast, and finish up with that 4th type of index scan. But that's it for today, and I will see you all on Wednesday.